Hello everyone, Mr. John here from Areteem Institute with this week's Thursday Tidbit, where we're continuing some 10 and 12 AMC problem review. Now, we are now 1 week away from the A dates, so great time to do some last minute prep. Check out our blog. We actually have a new post today talking about some timing tips, how to manage your time, things like that as well. So great way to do some practice. Check out the ZIML site for some mocks, monthly contest, things like that as well. But let's jump into our focus of the day, which of course is solving some problems here. So first problem is from the 2016 AMC 10A. Both problems are from the same year. This question actually was on both the 10 and 12 exams, talking about a quadrilateral inscribed in a circle of a given radius. So we have a circle with a set radius and three sides of that quadrilateral all being the same length as well. And we're looking for the length of the final side in this scenario. So let's start with a nice big circle here for our setup of the problem. And we want to start drawing this out, labeling some points, stuff like that too. Now, just to keep things organized, and diagram may not be perfectly accurate or anything, but let's have our bottom, the length of this fourth side here. And then we have these three sides of equal length on the other pieces there. So those three sides have the same length in this scenario. And we know that they're all of length 200. Let's not worry about that right here at the moment. We'll come back to that more later. But let's think about these three sides there, and maybe we can label our points as well. So natural labeling A, B, C, D around this way. And right, our main piece of information is that these three pieces all have the same length. Now, if that is something that you recognize immediately, that's great. If not, I'll explain it in a moment. But the thing we want to recognize here right off the bat is that this tells us that actually our three arcs. So we have these three chords. They all have the same length, A, B, B, C, C, D. In fact, that tells us that the arcs all have the same length as well. So the measure of arc AB is equal to the measure of arc BC is equal to the measure of arc CD. And this is actually going to turn out to be one of the important pieces of things that we can do with this problem here. So let's move this over a little bit here. And let's call all of these angles theta. Now, if you want to know how you prove that, in fact, we can draw this in the picture. This will be helpful anyway with our diagram. Anytime you have a circle, a good point to draw is also the center, right? So we have our center. We actually know the radius of this circle, so that's extra special here. But here's the key. OAB is a triangle with two sides of 200 root 2 and a third side of 200. Same for BOC, same for COD, right? So all of these triangles are congruent, meaning all of these central angles are congruent. But notice that those angles are exactly what we have for this arc AB, arc BC, and arc CD in this case as well. Okay, now we have a very important question that is the key to solving this problem. All right, so let's look at the following thing here. if I want to ask us about the measure of angle BAD, this will make a lot of things click into place then from here. Well, this is an inscribed angle, right? If we look at this angle here, it's an inscribed angle, and the arc is BCD. So the measure of an inscribed angle is half of the measure of arc. Let me just, for clarity here, write it as arc BCD. And what's important about BCD? Well, that's 2 theta. So this is 1/2 of 2 theta, which is, of course, just theta there. So this angle here is actually theta as well. So that kind of is what's important in this case. Now, let me label a couple of other points here. So we had A, B, C, D. Let me maybe keep going on here. We have this point here, E, and this point here, F. And here's where the magic is going to start happening. Now let's start with this side. You'll see actually that stuff happens on the other side as well. But let's start here with these triangles. So if we look at triangle ABO, notice that this triangle has it's an isosceles triangle with a kind of angle that's different from the other two, being theta. That's the same case for BEO. That has an angle of theta, and they share this angle right here, right? This angle is shared for both of those triangles, meaning that a triangle ABO is similar to triangle EBA. So that's kind of what we have here. And this is actually super important. Why is that? Well, now we can start looking at ratios, right? We know that OA is a radius. We know that, right, that is 20√2. And we also know AB is 200, right? And so this gives us a lot of kind of information there. In fact, both of these triangles then are isosceles, right? So this implies that ABE is also isosceles. So AB equals AE equals 200. So this is how we can come up with that length of AE in this scenario. Now, identically, this is equal to DF. So I don't want to spend too much time here. Those two triangles are congruent. So if this length is 200, DFCD is also congruent to that, or you could play the same kind of arguments there. This DF length is identical in this case too. So we have 200 and 200 there for DF and AE. So the final question then comes with EF in that scenario, right? And so we want to figure out here, what can we say about triangle OEF, right? Well, notice that that is also a similar triangle there, right? So that's similar, but let's take a moment here and think about what we can kind of say about BE in this case. So first of all, this tells us this was an isosceles triangle there, but we can actually also use this to kind of calculate some other pieces of information there here as well. Right, so what can we say then about BE? Also, we actually also know here, well, let's look at some ratios. Well, the ratio of BE over AB, right? So the small bottom, or the smaller bottom to the side, right? This is going to be the same as the bottom. So this would be AB divided by AO. So we also have this information here. Now, if we look at this, this tells us that BE, right? So this tells us then that BE is equal to AB squared. So AB was 200. So this is 200 squared divided by, well, then what was our radius AO? This is 200 root 2. So after simplifying, this is 200 divided by square root of 2. Or if you kind of simplify that there then, right, we get multiplying top and bottom by root 2, we have 100 root 2 as well. Now, on the surface, this seems a little bit, right, unhelpful, right? We might say, okay, well, why do we care that BE is 100 root 2 in this scenario? Well, notice that this is telling us the ratio of sides. This is half of BO, right? So I want to stress here on the bottom, right? Should be still visible here. This is actually OE divided by 2. So that ratio there, BE, is half of, not OE here, sorry, so this is actually equal to EO, or it's half of BO in this case. So that length is half and half here. So this allows us actually to finish up because we also know, and I already said this verbally, but let me write it down, OEF is similar to triangle OBC. And now we know the ratios are 1 to 2. So this tells us that since, right, we have this 1 to 2 ratio, EF to BC, so we look at that ratio, is the same as the ratio we just were looking at. Is the same EF to BC is the same as OE to BO. But since BE was half, this is telling us that EF is BC divided by 2, which is therefore equal to 100 there. So we've now found that EF is 100 in this case. Now, let's squeeze this inside of our triangle, or inside of our circle here. We're now ready to find AD for our final answer in this case. So AD is equal to then, well, AE is 200 plus 100 plus DF is another 200. So AD is 500 in this case. And that gives us our final answer of E in this scenario. So putting it all together, just following the angles, isosceles triangles, similar triangles, everything actually works out pretty nice, and that gives us our final answer, E, here. Okay, so let's look at our next question here. Again, one that's a little bit tricky, but actually has a nice intuitive answer, but we'll talk about some of the details of how to prove this as well. But this really starts out as a good practice with Vieta's formulas. So reading the question, we have a smallest positive integer or real number A, positive real number B. So let me just highlight the fact here that we have positive real number A, positive real number B, right? That is our information here that we're given at the top. And we know that the roots of this polynomial are real. So let's look here and see what Vieta's theorem says. So we look at our polynomial and standard name for the roots. So if R, S, and T are the roots of our polynomial, what does Vieta's theorem say? What is Vieta's formulas, theorem, however you want to think about this here? But Vieta's tells us 3 facts. So we can always start with the sum of the roots. So r plus s plus t is negative a. So that is a. So the sum of the roots is a. The product of pairs. So we start with adding up all the singles, then we add up all the doubles. So rs plus rt plus st. This is equal to positive b. So then we have b. And lastly, but not least, products of triples. Well, there's just one triple. RST is, again, we alternate negative, positive, but because we have negative a's there, we have the sum of the roots is a, we have the product of pairs is b, the product of all the roots is a again as well. So we have this kind of special thing that we're looking at here, right? We're kind of looking at, well, we have this sum of the roots is a, and the product of the roots is a there. Now, couple of notes. I'm not going to write this down, but if a and b are positive real numbers, right, all the roots are real, right? So we have a bunch of kind of positive numbers that we have here too. So actually, I think it's good to write this out as well. So actually, all of these are each greater than 0 as well. Now, why is that worth mentioning? Well, we can start thinking about here some kind of geometry type things, right? So RST is the volume of a box with sides R, S, and T, right? And we want the kind of smallest thing that we have these kind of roots and stuff like that there. Now, I want to mention this, but I do want to talk about it intuitively. We will do a more formal proof quickly, right? But intuitively, right, in these types of things, right? So, okay, we have a rectangle. We want to look at the perimeter so that we have the biggest area, right? Oh, it's a square, right? We have these symmetry type things going on here. So intuitively, we would like to say, and it should make sense, that all of these roots are the same, right? We have this kind of minimum, all of the roots are real. It's a triple root then, right? We have a very simple polynomial, stuff like that in this case. Now, how would we prove something like that? Well, the proof is actually using the AMGM inequality. So if you're not as familiar with this, we do have an old Thursday tidbit talking about that a little bit here, but it's kind of intuitively doing what we're saying, that all of these should be equal, right? So we have that the average of the 3 numbers, this is where they all are positive numbers, comes into play. This is greater than or equal to the product of the 3 numbers, cube root there. So what does this say in terms of our stuff here? Well, the product, or the sum is a, the product is a in this case. So this tells us that a is greater than or equal to, multiplying both sides by 3 cubed root of a there. All right, we have all positive numbers, so cube both sides, divide by a on both sides. This tells us that a squared is greater than or equal to 27. So this tells us that a is greater than or equal to 3 root 3 in this scenario, right? And where is equality, right? Remember, equality happens when the 3 numbers are the same, right? So the smallest a is a equals 3 root 3. And right, this happens when all of the numbers are the same. So r equals s equals t. And this one's pretty easy. So how do we have, right, the product of three numbers is 3 root 3. Well, if we write that as a kind of exponent, this is, right, 3 raised to the 3 halves, or we're summing three numbers. This is evenly divisible by 3 as well. Pretty easy that kind of r, s, and t equal square root 3 in this case. So this is how we kind of put everything together then there. And that is the proof, right? So intuitively, r, s, and t should be equal. And then you could use that to find they're all square root of 3. So if you have this shortcut, that is fine. But the actual proof of it is using AMGM there. Now, pretty easily putting stuff together to finish. Well, b was the sum of these pairs there. So b is equal to root 3 times root 3. So this is 3 plus 3 plus 3 is 9 in that case. So not too bad, plugging in, again using Vietas, right? So I don't want to get distracted by this AMGM stuff. The real key here is this Vieta's formulas, and we get our final answer. B is 9 in that case. Okay, that is it for this video. As mentioned, right, check the links below for some other resources for access to some timing tips, last minute practice for the AMC exams if you're taking them next week. Otherwise, I hope to see everyone back next time for some more problems. We'll do a final video for the practice, and stay tuned for things like solutions between the A and B, stuff like that as well. See everyone next time. Goodbye.